So I'll start.
Just a minute. Let me at least talk. Let small introduction, and then your turn. Right. Okay. So we are today welcoming Professor Madhava Krishna from IIIT Hyderabad. Specifically, he's the head of the Robotics Research Center there. So Professor Madhava Krishna studied in some of the top institutions in the country in India, and for his postdoctoral research, I think PhD was at IIT Kanpur, right, Madhav?
Yeah.
Correct. Yeah. So, and then postdoctoral research, he spent some time in France, and he was not happy with that. He thought he should come back to India, build his own empire. So he decided to come back.
I mean, if you want to say that, I also spent time in US. You should be equally.
Equally bad about the US as well.
And in US.
Yeah, and in US, he was not happy with either one of those. And then he decided that he had to build his own empire. So over the last 20 years, he has, I would say, at least my feeling is, at least partially succeeded. The Robotics Research Center publishes in some of the top places, like, they have multiple papers in ICRA, CVPR, and things like that each year, which is like not an easy feat at all for those of us who work in this area. And they do some really interesting work. And I have known him from the time I was a graduate student, right, in Texas. And so from the bio, as you can see, I mean, the Robotics Research Center, in addition to doing cutting edge work, is ranked very well internationally. And so I'm sure he will talk to us, and this will be really interesting to a lot of people here. So thanks, Madhav, for agreeing to talk today, and I will give it over to him. Madhav, go ahead.
Yeah, sure. Yeah, thank you. Thanks, Mohan. I hope I do stand up to your expectations. Yeah, it's been a long time since I talked, and maybe the last time was in ICRA 2017. What I mean to say is for an international audience. So I've been here for 16 years, not for 20 years. Whether it's an empire or not is not, I mean, like, that's up to you to decide. So at IIIT Hyderabad, so I've been working on a bunch of problems, and one of the key areas has been in robotic vision plus machine learning, often dovetailed towards driver assistance, which is to say, like, on-road scenes. A bunch of other things also which we do in vision and ML, but I'm not sure if we would be able to cover all of that here. So at some point of time, we did have a self-driving car. Because of the pandemic, we have not been able to use this for almost a year. But I heard, like, yesterday, we got to start using this car once again, on which we have done some, we have managed to do some state-of-the-art research on these kind of vehicles and at least publish in reasonable places. So we also work with drones, vision control, and things like that. And also, though this is not my area at all, so the students who work with me have managed to come up with very novel mechanisms like this, a pipe climber, which is climbing a pipe, stair climbers, and things like that. So for a long time, I was alone, but now suddenly we have 3 more faculty, one who is specializing in mechanism design, another person is more of a classical control plus robotics person, and one more in UAVs, more towards fixed wing aircraft. So we do have a team right now, which was missing for a long time during. I was possibly the sole ruler, and now we have more to share. We believe we have been working on difficult problems, and one thing which we have been able to persistently show some kind of output or productivity is what we call as this dynamic scene reconstruction, how to reconstruct a scene where there are many moving agents with a moving monocular camera. And I would say, like, why this problem is kind of very tough, and what's really interesting and challenging there. So we've also worked quite a bit on category-based visual servoing, wherein we servo to an object category rather than to an object instance, and to objects which have not seen before, we are seeing for the first time, but I'm not getting into that in this talk. And then this is something which we have recently been working on, to use language and vision to guide robots and things like that. So I'll start off with SLAM, and then I will go towards motion detection, come back to SLAM. So this is the SLAM problem. So you have a 3D point such as PJ, but what we don't actually know where this point is, but what we see is a set of observations of this 3D point on the 2D image in terms of its pixel location. at an instant k-1, k, and let's say k+1. So we make these observations on this point, and then we try to do two things here: estimate the camera motion as well as to be able to reconstruct this point. And then this reconstruction has an inherent scale ambiguity. As we move forward, we'll just touch upon that, right? So the SLAM process or the pipeline is very well known. So there are many variants to it. So this is one of the standard variants. Like from two views, you have correspondences across the images in two views. It could be from SIF, SURF, KLT trackers, optical flow, whatever that may be. From there, we compute the so-called fundamental matrix and then the essential matrix and decompose the essential matrix to set of R and T, camera extrinsics, as we say. And then we reconstruct the scene from two views, and this will be up to scale. And in the third view, we make use of the reconstruction up to two views and the points in the image that are being tracked in the third view to solve for what we call as the camera resection, which essentially gives the third camera pose in the same scale as the second camera pose. So this is an important thing which we do in SLAM. And in general, the nth view we obtain by the nth camera pose, we obtain with respect to typically either the first camera or the n-1 camera by solving the PNP problem of all the points seen so far up to the nth view, and those points of the 3D which are observed in 2D in the nth image. So we use this and we get what we call as the SLAM front end. By this time, we have a reasonably unstable trajectory as well as a 3D reconstruction, which is typically sparse. And then we do this final optimization, what we call as the backend bundle adjustment, to get better estimates of the camera trajectory and the reconstructed points. So this is a simple illustration of this process. There is a Parrot AR drone happened a few years back. And then it's moving around the mud. It has only a monocular sensor. And so we use this Raptor and PTAM for this. It's not our own SLAM backend here. And then we track these 2D points and we finally manage to, as we move forward, we manage to get this drone trajectory as well as the reconstruction of this 3D mug. Of course, this mug is not in the original metric scale, but this is actually in some scale, but it's a consistent scale, which is to say that the scale is just one single transformation from the actual metric scale, so to speak. Now, the challenge, however, is in dynamic scenes. So as we could see, like there was a car that actually moved past, and then we have the image of this car observed over several cameras. But if you actually try to triangulate this car, which is what we do in SLAM, suppose I managed to compute the fundamental and essential matrix of this entire road scene along with the car. And then assuming even if this estimation was correct, if I try to triangulate, so because really the car was not stationary and it was moving, so this triangulation is really going to be erroneous. So you get this meeting point here, whereas the car was on the road, because you cannot really triangulate a moving car from a moving monocular camera. All you could do is you can only do bearing only tracking, because and therefore this problem is unobservable. So which is to say that there is an inherent intractability of reconstructing moving objects with a moving monocular camera. And so we can only say the bearing at which you are seeing this object. You really cannot estimate the trajectory of this object with respect to any known coordinate frame. And this is the traditional problem in dynamic scenes. So I will move, I would say, like how we have been tackling this for quite some time now, and then how we have been tackling in the post-modern era or the deep learning era, and what are the challenges that still remain. And all the work which I'm showcasing here is, of course, done due to my fabulous students who have somehow been with me over the long period of time, and then have been managing to produce these very good papers. And they've also moved on to very good places, and they are doing generally well, I would imagine. So we'll start with what I call, like the way to now approach this problem is in dynamic scenes is one has to first at least minimally filter off the dynamic objects. And so how do you know an object is moving or not, or how do you know a pixel in the image is moving or not? So that's the problem of motion segmentation. So I'll kind of explain a little briefly as to how to do it when the camera motion is known or the camera extrinsics is known and when it is unknown, and then quickly pass on to how one could do it. One could obtain a dense motion segmentation and what that means, and the challenges in motion segmentation itself with a moving camera, the problem of degenerate scenes. And then I will move on to motion reconstruction and how we solve this problem with the classical formulations with SLAM and things like that, or what we call as multi-body SLAM, and the challenges there, and how we moved on to semantic SLAM, and then SLAM with shape priors and what we call as the postmodern deep learning era, where when we are able to reconstruct this object with a single view, and then how do we make use of single view reconstruction that's possible for objects in the deep learning era, and what does that mean to the SLAM problem itself. So I hope I can touch upon all this as we move forward in this course of this talk. So there is a bunch of publications which we have. So we don't typically publish in CVPR or ICCV. So it's mostly in ICRA and IROS, which we have. So this started with IROS 2009. And luckily, we have been managed to keep showing something in this area to as recently as ICRA 2021. And these are the bunch of people who have actually developed this area. So Abhijit Kundu, of course, is currently in Google Research. So just to say where these people are today. So this is Abhijit Kundu, who is in Google Research and previously was with Georgia Tech. But one thing which we are quite happy to note is they continue to talk about us. And then if you see their publications, you would find that there is a fair amount of things which they have done with us, right? So for example, these are publications with us long time back. So these are, and same with Dinesh, he continues to acknowledge us. And then, like if you go back, so these are, so up till here is something which he had done with us. And these are things which are new. He is doing his PhD in CMU. Of course, Krishnamurti is the big guy. He's in Mila, and so he's supported by an NVIDIA graduate fellowship. And I think he's one of the few guys to have rejected a Google PhD fellowship because he already had an NVIDIA grant. And if you look at his publications as well, you would find that there's a lot of things which he had done with us, such as these things, right? So just to say, like, somehow I've been fortunate that these kind of students came and worked with me and, advanced this field, hopefully, and they're doing well wherever they are. So the first step is, if you want to do SLAM problem in dynamic scenes, the thing that comes to our mind is, can we filter off these agents which are moving? And which is to say, in a sparse SLAM construct, it was to kind of say, can I filter off some of these featured points? In this particular case, they are these KLT trackers. How do I know if a KLT corner feature is it a moving pixel, or is it a moving feature, or is it a stationary feature? So how do you attempt this problem, right? So this is the first thing which we did, detecting moving objects from a moving monocular camera, wherein we assign to each feature a probability of it being stationary or moving, and then we cluster all these moving points or pixels to a convex cell and say this area is moving. And of course, it has a lot of applications. And why is it tough? So for a moving camera, everything appears to move, including the stationary world and including the moving world. And it's quite impossible to compute the relative velocity of the object from 2D images. It's not possible to say whether the object has a similar relative velocity as the camera. I cannot have any idea of how the object is displaced in space, because I can't reconstruct the object, because that's an intractable problem, as we have seen, right? So it's not possible to come up with any velocity estimates for the object in 3D, because without reconstructing the object. And if you want to reconstruct the moving object, it's ILPO. So it's a chicken and egg problem. So we need to compensate for the camera's own motion to solve this problem. And so how do we do that? In the first framework which we did, the camera motion came from the robot's odometry itself. But having done that, so how do we go about it? So, right, so given a set of KLT tracks obtained from an image sequence and the robot odometry, we estimate the fundamental matrix or the essential matrix. And then we look for two constraints. One is the epipolar constraint. And based on the epipolar constraint, we assign a feature probability as to whether this track or this feature vector which we are tracking, is it a moving feature or is it a stationary feature? We kind of compute its probability based on epipolar constraint and also another constraint which is called flow vector bound. And based on this probability, we cluster features belonging to highly dynamic regions, and we then get the motion regions from it. So there is this synchronization. We need to correctly estimate when the camera motion is happening, like when you're synchronizing the camera frame grab at pretty much around that same point, we should be able to have the odometry estimate coming from the wheel encoder. And once we do that, so this is the basic idea. So there is a point P observed in two cameras, C and C dash. So this point P projects to X in C, and it kind of projects to X dash here. And this will lie on the epipolar line corresponding to P. Right, so this when P projects to an X dash, if it was a stationary point, then this epipolar line is the line that is and the image of the 3D line which is joining the previous camera to this 3D point P. And so this projected P in C dash would lie on that line. But however, if this point were to move, right, P move to P dash, then this X dash is not going to lie on this epipolar line. And so you can kind of take the perpendicular distance from X dash to this epipolar line and use that as an indicator of whether this point is moving or not. And you can get this so-called epipolar error and things like that. And so this is Abhijit Kundu, who is in Google research, and this was something which he did in 2009. And so these are the points on his own body which are moving, which have a huge epipolar distances. These are the feature tracks of the point coming from a KLT tracker, a sparse optical flow. And the rest of these points are actually very close to this epipolar line. They don't have because they are stationary points, whereas the moving ones have a huge displacement from this line. And we make use of that to solve for whether a point is moving or not. However, there are some set of points which can move, like this point P can move to P dash, but it moves in the so-called epipolar plane. And when it moves in this epipolar plane, even though this is moving, the projection of it will continue to lie on the epipolar line. So a point can move, but it will appear to satisfy the epipolar constraint. And this is a degenerate motion. And this is kind of tricky to, so this would appear to be stationary, while in fact it is moving. So it's appearing to be stationary from the point of view of the epipolar constraint. So we came up with this so-called flow vector bound, or rather Abhijit Kundu came up with this, wherein he, assuming that we know the depth to this point, which we don't know. So assuming that if I know a depth to this point, and even if there is rotation, in this particular case, we are not showing what happens when the camera rotates, but even if the camera rotates, this equation would hold. So you can predict where this point would be in the next image, right? If based on this depth. And so if this equation is not obeyed, then we could assume that this point is moving. But we don't know Z, so we assume a bound in Z, like Z min and Z max. So for a minimum and maximum bound, we can have the minimum and maximum displacement of this point based on this optical flow equation, which we just saw. And if this point lies outside of this bound d min and d max, then we think that the point is moving. So combining this epipolar bound constraint and flow vector bound constraint, so Abhijit managed to, integrating with a probability framework, he managed to do something really very cool. So this video is a little grainy because I think it's been not the original video, but this is a 2009 video, and it would still cause some very some kind of an wow effect. So that's the moving camera on top of the P3DX. And there are other agents which are moving in front of it. And you could see like we have managed to segment all that is moving. So this robot was moving. Abhijit Kundu himself is moving here. And you see that the camera is also moving because you see that the floor is moving. These objects are moving as well. So the entire scene is moving, as you could see, but we are able to track the moving agents on this. And this, of course, has a lot of citations today, this paper. And this is from a point of view of P3DX, wherein we don't need to solve for the fundamental matrix and essential matrix. They are coming from the odometry. We use the odometry to solve for this. So this is one way of helping SLAM, in the sense we are able to filter this moving object, and then we can use the remaining part of the image for doing this stationary SLAM. That's one way. And then I think we also did it even when, for example, for example, in this video here. So in this particular case, this is an outdoor sequence, so we don't have any control on how the camera is moving. So from the stationary tracks, we managed to estimate the camera motion. And once we have estimated the camera motion, we have been able to filter these moving points. So these are the points which are moving. And we are also able to get a bearing to that point. We kind of say, like, with respect to the camera, what's the bearing of that point. Right? So this is from a known camera and from an unknown camera as well. So we can do. And then we did it with dense motion segmentation. So if you saw the previous thing, we were getting sparse features, but with a dense optical flow, with a similar pipeline, which I'm not getting into, we managed to get a dense motion segmentation, which I can show the video here. Some of these videos do not play on my Mac anymore. They are rather old, but so this is the idea. So this is the object that is moving, and the camera, of course, is also moving, possibly a bit slow here. So we have managed to segment this motion densely, and all with very classical methods. So this is a bunch of students who are moving, and the background is also moving, maybe a little bit slow, and we are able to segment all the moving objects. In this particular case, I think this is a scene from UK itself, a CamVid data set. And so the camera moves because we see that the stationary world is moving, but we have managed to segment through this dense optical flow and the combination of epipolar constraint, flow vector bound constraints, and few more heuristics. We were able to densely segment the object that is moving. And so this one thing, like, these are, I would call as evergreen movies. This is a movie from 2012 ICRA, but then when you're seeing it today, it's still, I hope, is creating that, okay, I know, like, it's a cool movie. And it's not easy. If you ask me to reproduce this result today, it's not so easy. I mean, it may take us at least 4 or 5 months to really be able to do it, because it's not straightforward to get this thing. And this is, I think, on Versailles Ron sequence, wherein once again we are able to densely segment motion. So all this with the idea of, once you segment these dense moving objects, then we can use the remaining part of the world to do SLAM, and that SLAM would be less noisy because it's not corrupted by the moving parts. So the minimal thing is to filter the moving objects and do the SLAM on the stationary scene, but then that's not reconstructing the moving objects in. So yeah, please feel free at any point of time to stop. And if I do remember what was exactly happening here, I can try to say. But Otherwise, I can point to the papers or to my students who can also explain certain things here. But this motion segmentation had problems. So for here, like we were not able to get any motion segmentation on these cars for whatever reason. This is a data set made available to us from Nissan. This is from Japan, and somehow things are not working. And one thing which we figured out was we need to get a very good camera motion estimate. And if your SLAM backend, which is actually, or the SLAM front end, which estimates the camera motion, if that's not really doing a good job, then we have a problem. So sometimes things don't work, also because the feature tracks are not stable. And so then I was thinking of, like, can we get the environment into play and try to bypass compensating for the camera motion? So can we do it without that? And what I was looking at was, like, suppose, let's say there is this car and which moves away. And even if the camera is moving, so this car's relation with respect to these points in the stationary world, so they undergo a lot of significant shear. But these points themselves, between these two images, these green points within themselves don't have a big shear. These red points within themselves would not have a big shear. If you kind of try to estimate the relation between the red in the current view and the red in the previous view, they have a very similar shear. But between the red and the green, when there is a motion relative to a stationary world, there is a shear. And can we use this shear to somehow segment motion without having to compensate for the camera motion? So this was the idea here. So what we did here was, like, we decompose the scene into a lot of affine models, affine motion models, which is to say, like, the way we did it was we still use the epipolar constraint to segment the background, and we try to get a lot of background points. And then we cluster over segment the background into a lot of affine models, affine motion models, which is explained in the paper how we do that. And then after that, we use some long-term motion coherence and temporal smoothness and some of these kind of clues to pull together some of these motion models into a more unified model. And then finally, we make use of this shear and stress clues to come up with the actual motion. So if you see this background belongs to one motion model, and these cars belong to another motion model. And this was done, and here, so I can just show this video as to how we were doing this. So this is the track from a KLT tracker. It could be a dense optical flow, and this is the initial affine motion models. So which we have a over-segmented motion models here, and so using some long-term motion coherence and things like that, we managed to, with this energy minimization framework, we were able to pull together some of these motion models. And this is the final result, wherein we have the stationary background and the moving foreground. And how did we do that? So how do we merge motion models? So right now here, at this point of time, so you have 1, 2, 3, 4, and 5, five possible motion models. And we will end up merging 3, 2, 4, 5 together, but one would stand apart, right? So how do we do this? Is so we check if there is a lot of shear between 1 and 2. So 1 versus 2, there is a sufficient shear. So we don't merge 1 and 2. But between 2 and 3, there is not much shear. So they across views, the shearing is not a lot. So we end up merging them. So between 4 and 5, once again, we say that the shear is not so much. So we merge them. But between 1 and 4, we say that there is a significant shear, and so we don't merge it. And once again, between 2 and 4, there is insufficient shear, so we merge. And therefore, we manage to get this kind of background, foreground, or motion model, so as to speak, using shear as a dominant clue. How does this relate to the remaining points? Do we have a lot of shear between these points and these points? Yeah, over a set of images, right? So this is basically we bypass the need for the camera motion estimation, but these are still in the realm of motion segmentation. I will bypass this, wherein we combine semantics and motion and talked about this, but I will go to the problem of SLAM in dynamic scenes and just touch upon how it is done and what indeed is the challenge here, right? So one of the challenges we have already seen, what we have talked about is we can't really reconstruct the moving object from a moving monocular camera. Then how do we end up doing it? So at this point, we assume through all the any of the methods which we have seen so far, we are able to segment the moving objects. So that's the idea. So we are able to use one of those methods to segment this moving object. And then what do we do, right? So, but before that, so what we want to see is something like this. So we would like to estimate the camera motion. We would also like to estimate the trajectory of the moving object. And we also want to estimate the 3D points. Of course, they are sparse, but in terms of where they are in the scene. And so we would like to do all of this together, right? So, so how do we get this kind of result? That's the thing here. So this is the system should output all the objects which are moving, and we should be able to reconstruct the stationary points in the world. We should also be able to reconstruct the moving points, the pixels on the moving object. And we should also be able to estimate the camera trajectory in 3D. And so this is the overall idea, and we should be able to do it with a single camera. And of course, this we have seen the same thing, which is to say we can't reconstruct a moving object from a moving monocular camera. So what we did in the first moving, so we did this what we call as particle filter framework. So which is to say, the way this algorithm works is after we segment the moving object. So maybe I'll just play the video to. So what we do here is so we have segmented this moving object and we have segmented the stationary world. So we have now, like these points are on the stationary world and these points are on the moving object. And now we do a SLAM backend with respect to the stationary world. So which is to say, like we estimate the camera motion with respect to the stationary world, and we get a camera motion with respect to that, and we get a reconstruction of this stationary world. And we also reconstruct the camera motion with respect to the moving object. So what we do is, because we have segmented this moving object over multiple scenes, so we have just that moving object with us, and we try to estimate how the camera is moving relative to this moving object. Or equivalently, assuming that the camera is stationary, we try to estimate how this moving object is moving with respect to this camera, which we assume to be stationary. Okay, and because we know how the camera is moving with respect to the base frame, because we have done the stationary SLAM here. And if I know how the object is moving with respect to my camera, assuming that the camera is stationary, it's only a simple vector addition that I should be able to get this. However, the only problem is the motion estimation or the reconstruction of the moving object with respect to the camera or the camera motion with respect to the moving object is not in the same scale as the camera motion with respect to the stationary object. So which is to say, in other words, the reconstructed points with respect to assuming that the moving object is stationary and the camera is moving, so these reconstructed points and the stationary world reconstructed points, they are not in the same scale. And so it's difficult to place this, we don't know in what scale it is with respect to the camera trajectory, which is estimated in the stationary ground frame. So how do you, though we have this reconstruction, but this reconstruction is in a scale of its own. And though I know where it is with respect to my moving, with respect to my camera, that where it is with respect to the camera is in a different scale than where the camera is with respect to the ground. So I can't add those two vectors. So this is where the camera is with respect to the ground. So I have the trajectory of the camera. We are always getting the camera trajectory as we see here. So I know where the camera is with respect to the ground. I know where this object is with respect to my camera. However, I can't add these two vectors because these two vectors are in two different scales. So this is the classical, we can't get over the observability problem because it's intractable. The same observability problem, which we said, like we can't triangulate a moving object from a moving monocular camera, comes up in this way, right? So now in the first thing, what we did was we assumed that we didn't really actually so having reconstructed the moving object with respect to the moving, assuming that the camera is stationary, and then having known how the camera is moving with respect to the stationary world. So we used a particle filter framework and we tried to figure out what could be the best hypothesis of where the object could be with respect to the camera in the same scale. So as the camera is with respect to the moving, with respect to the stationary world. So these particles here are different scales at which the object could be. And then assuming that where the background is with respect, I mean, like we know, for example, this object cannot be more than 5 meters away because we are seeing a wall behind and things like that. So based on that, we managed to kind of estimate some probability of the scale of the of the location of the moving object with respect to the camera in the same scale as the stationary world. So sorry if I'm I'll possibly explain that as we move along. So, right. So this was a particle filter way of solving that relative scale problem. And I would show what that means here. And then we came up with an analytical solution here in this particular case. So this is the basic idea. So if I would hold right. So I segment the moving object and I get the camera trajectory with respect to the moving object. And so having segmented this moving object, I get the camera trajectory with respect to the moving object and the reconstruction of this moving object itself. And on the background as well, I get the camera trajectory with respect to the background and the reconstruction of this background. So if I know how the camera is moving with respect to this object, I can equally say how the object is moving with respect to the camera, assuming that it is stationary. And because I know how the camera is moving with respect to the stationary world, I just have a vector addition. But however, there is a scale problem because those two, you can't add those two vectors because they are at two different scales. So this is the basic problem. So how do you solve for this relative scale, right? So this is the main idea. So finding the relative scale for each moving object, the problem of relative scale occurs in a multi-body setting when the reconstructed points of the stationary world and moving objects are to be represented in a unified frame of reference. And there is a scaling transformation between the objects in the object frame and the stationary points in the world frame. And this transform results in a one parameter family of possible trajectories. So, and this is what we call as the relative scale between the dynamic reconstruction and the stationary world reconstruction, or the camera trajectory with respect to the dynamic scene and the camera trajectory with respect to stationary scene. In whichever way you look at it, so there will be the scale problem. And so if we do not solve for the scale problem, so what can happen is, so I can, if I just fuse it arbitrarily, or I just fuse it without solving for the scale, then while this should be the true scale, either this object can appear to have sunk below the ground, or this object could have appeared to be floating in the sky, this moving object, they would not be well grounded. Okay, so this problem would be there. And so we actually solved it. So we need to restrain the moving object. So we need to know some prior idea of how the object is moving. So we solve for the scale problem analytically for two kinds of motion. One is where the moving object is moving in the same plane as the camera is moving, or the moving object is exhibiting a non-holonomic motion. So this is there in this ICRA 2013 paper. So we now have an actual solution to this scale problem, and then we seemingly seem to have solved this. So we see this, so we are getting the camera trajectory. We are also getting this moving object trajectory. So there is this camera which is flying, and a drone which is flying with respect to the camera. So we have reconstructed the bed, and we have reconstructed the drone, and all seem to be hunky-dory. So there's a P3DX which is moving in front of a moving camera, and we have managed to reconstruct this P3DX as well as the stationary scene. We managed to represent all in a unified frame. So we are also estimating this camera trajectory. And so the problem seems to have been solved, but we were not happy. Now, what does that mean to say that we are not happy? Is the chance of this working, this complex pipeline starting from motion segmentation and then reconstructing the moving object, or estimating the camera motion with respect to the moving object, estimating the camera motion with respect to the stationary world. And now we have two slams here, one with respect to the stationary world, as a matter of fact, and one with respect to every moving object. And now we have to fuse both these reconstructions in one unified scale and show it. The chance of this succeeding, it does succeed, provided the student has to do what as we call in India as tapasya, or austerity. So he has to really, like a monk, work and do a lot of data analytics and find out one particular result where it works, because there are so many things that can break. Because anybody who has worked with SLAM systems know there are a lot of chances to fail, right from the fundamental matrix estimation, essential matrix, because it is a combination of several nonlinear optimization problems. And on top of that, we are also having motion segmentation, motion reconstruction, solving for the scale analytically. Unless things are precisely there, you don't get this this analytical solution to the scale, and so we don't know. We can't say like whether we can actually get it to work. So if somebody comes and says like, will it work on this scene? We are not sure. So people can ask like, well, you have a few papers, but why are you not sure, right? So it's not like because we have cooked together a cock and bull story, we're very sure of the formulation. It's just that the formulation, getting it to work is not so repeatable. So this was where we were around 2013, and then we moved to stereo SLAM, because then we don't need a monocular camera, and we get the stereo reconstruction. And then by that time, there were like CRF models and things like that, which were getting, object segmentation. And so we did the semantic SLAM, wherein we have reconstructed through stereo the stationary world. We have the semantic segmentation of the ground plane. We now know the semantic segmentation of a car, and with stereo we have a reconstruction of the car. And with some kind of ICP, we know how the camera is moving with respect to the stereo point cloud. And then we solve for the backend optimization in bundle adjustment. Maybe I didn't say how the backend optimization is solved, which is over M frames and N 3D points. We try to estimate the camera motion and the reconstruction, having an initial estimate of my camera motion and the 3D points itself. And typically it goes through an error minimization, which is in terms of reprojection error. So we minimize the reprojection error for every 3D point as it projects to every image, and then sum it over all the images which you have seen, and we re-estimate the camera trajectory and the 3D point itself. Along with that reprojection error minimization, we can give a lot of the semantic constraints, which is to say that this camera motion should be normal to the ground plane, because now we know the semantics. We have segmented the ground plane and we know the normal to that. And then we can say that there should be a smoothness, because this is a car which is moving. It can't have, it can't move abruptly. And because we know this is a car, so we say that all the points in the car should be bounded within an object of some size. So we can give all these kind of constraints along with the regular reprojection error constraint, which is what is there in a SLAM framework. And so we combine this semantics with SLAM in this particular case. But this is not a monocular SLAM. So this is a stereo SLAM, so as to speak. So wherein we reconstruct the world, and the camera trajectory itself is estimated simply with ICP. And we are not actually doing a stationary SLAM here, but what we are trying to do here is making use of the semantics to improve your ICP computed trajectory with respect to the stationary world. And also we are trying to improve the reconstruction of this car because we know that this is a car. And and things like that. So we integrate that into the backend optimization. Of course, it's a SLAM because we finally do the backend optimization. The front end, of course, is coming through an ICP with respect to the stationary world. And so and so we have this as the input image. So we are getting the camera trajectory. We are getting all these moving object trajectory, all estimated. Because there's a stereo, there is no relative scale problem and all that. And we are also able to get the moving objects trajectory. Here the trajectory alone is shown. Here the 3D semantic map is shown. Here the 2D semantic map is shown. As a matter of fact, this is even before the deep learning-based semantic segmentation took place. This is a CRF-based semantic segmentation from Philip Tau's group. So that's the basic pipeline which we used, on top of which we did this SLAM. And then you could see that we are able to get the trajectory of the moving object and things like that quite well. And so what's the kind of time I have, Mohan?
We don't necessarily, I mean, we said you could speak for about an hour. So if you go strictly with that, you have around 10 minutes more, maybe.
Okay. And how much can I exceed that?
No. So usually our seminars go for an hour and a half. So
okay.
Up to you. You want to leave time for questions, how you want to do it, I leave it to you.
Okay. So yeah, so this is this so far was without all this machine learning, and then we started with how to get in learning into this framework, because we were not essentially the classical framework for moving object reconstruction fails. So, which is to say, when I segment the moving object and try to estimate the camera motion with respect to the moving object, that's the first step in this multi-body SLAM that is very iffy. So we started to use these kind of deformable parts models, so which is to say that I have a mean wireframe model. So maybe instead of going through this, I will say now how do we do it in the modern era. So far was the classical era. So, and let me try to see if what we do here. Okay, so so what we say is nowadays, like, we have a lot of 3D CAD models which also work on the real world. So you could have a 3D CAD model for a car. You could have a 3D CAD model for an object category, like a car, like a table, like a laptop, chairs, bottles, and things like that. So so each CAD model one can think of as an agglomeration of some key points. So a car can be represented as 36 key points corresponding to left wheel, right wheel, front wheel, rear wheel, rear view mirror, back view mirror, the top 4 roof points, and things like that. And each such point is represented in 3D. So as much as an image can be represented by a single vector, so we can have this 3D model of a car represented as a single vector. And then as I get more and more such models for a particular, for the category of car, I get several such vectors. So each vector could be like 36 cross 3. So 36 key points, and each of them 3-dimensional. So I have a 108-dimensional vector for one particular car model. And then I have many such vectors. So from that, I can do a PCA, so as to speak, and get a mean model. And then I have a number of basis vectors and the basis shapes, which are the eigenvalues corresponding to that. So any vehicle now I can represent in 3D as a combination of a mean vehicle plus a linear combination of its basis vectors. So this can be done, and so we can represent this car like this. So with this modern era, so we can start imposing this prior models for car, which we were not doing it in the classical framework. So right, so this is so I can have a 3D model for this car like this, and then and then I can represent a mean car something like this, is a combination of these 36 key points. And and then each car can be represented as a mean shape and a set of basis vectors. So it is enough to learn about 10 to 15 basis vectors at max. So we are showing up to 40 here, but really you don't need. So you can represent it in the low dimension space of 15 vectors, right? So and so this, so we can represent this as a mean shape plus a combination of these basis vectors. And then for every particular model of a car, so this is going to change, this lambda, and then the car deforms like this. Okay. So this is on the 3D side, and on the 2D side as well, we can train a kind of, there are many key point networks like stacked hourglass and many such networks, which can learn 2D key points on this car. So we know where these, so we can now learn a network to get these 2D key points. And as far as the 3D key points are there, so you could represent it as this mean plus a basis vector combination. And then we can still solve for the same reprojection error term, which I didn't actually show somehow. So this is the projection matrix, and this is the normally x minus x hat times the projection. So this is the error which we are trying to minimize. So this is the projection of the 3D point, and this is the estimated location, the prediction of the 3D point on the 2D image. right? So basically, so this is actually the observation, so as to speak, and this is the projection of the 3D. And we want to minimize this reprojection error term. So that's the standard way of solving any SLAM problem. And then we solve it over multiple views and for multiple 3D points. But in this particular case, we only solve for these 36 3D points. And we're not solving for the actual 3D locations. We are solving for the shape parameters or the eigen values corresponding to these eigenvectors. And when we solve for this eigenvalue, we actually recover the 3D shape for the car, which is consistent with the 2D key points which we are observing from the deep network. So the way we do it is we first, there is still an ill-posedness. We can't solve for both the eigenvalues and the pose of the car with respect to the camera. So we first solve for the pose of the car, which is how is the car oriented with respect to the camera, such that it minimizes this reprojection error. This is not needed because this is the camera intrinsics. Is slightly complicated notation. We just call it k times rx minus x hat, right? So and in the next time we solve for the shape parameters. So this is the same reprojection error term which we see in any SLAM framework, represented in terms of the basis shape parameters. And then once we do that, we now surprisingly get some really good reconstruction, which I would show, right? So this is the network which is giving the 2D key points and then the 3D shape. So this is the 3D shape, which is consistent with the 2D key points which we are observing from a deep network. And we are actually getting a very good estimate of the depth of the car with respect to my vehicle motion. With respect to my camera now, I'm able to say, like, how far is this car? So at least I'm able to reconstruct the car. We are able to see this wireframe, which is the reconstruction of this 3D key points, which is aligning quite nicely with the 2D key points which we are observing. And we are able to get the depth of this vehicle as well with respect to this thing. And so this is, however, so there is still a problem. This is still not the complete SLAM problem, because all we are getting here is where is the vehicle with respect to my moving camera. Okay, and this vehicle location is now appearing in the metric frame itself, because your 3D shape model which we are using was in the metric frame. Any CAD model is typically almost in the metric frame. So we get it in the metric frame. Also because we assume that in this particular case, we know the camera height, and so your initial estimate of where the object is with respect to the camera is there in the metric frame. So we get this reconstruction of the car and the depth of the car in with respect to the camera which is moving. But my camera motion is, let's say, is coming from a SLAM backend, like an op SLAM or one of those stationary SLAM. So that is not going to be in the metric frame. So you still, this problem is, while we get some really good reconstruction of this vehicle, and but however, I cannot still say where this vehicle is with respect to the stationary world, unless I estimate my camera motion in the same frame, in the same metric frame. But my camera motion with any monocular SLAM framework is not going to be in the metric frame. It will be in some scale representation, because there is this so you will only get an up to scale recovery of the 3D world, 3D stationary world. And so I still cannot say where this car is with respect to any ground frame of starting camera frame. If I only did faithfully monocular SLAM. Of course, if I get GPS and all that, I would be able to say, right? So that's still from the point of view of a monocular full-fledged dynamic SLAM problem, this ambiguity is there. The relative scale ambiguity, which I was talking about, which we did with particle filter in this 2011 ICCV and with analytical solution, forcing the planarity constraint and all that. So that problem is still not resolved. But we went on to solve other problems. So like how do you reconstruct this car on slopes? Normally when we so this is another challenging problem, because when we solve for this so when we initialize this t vector here, so this t vector is typically assumed to come because we know the camera height. We typically assume where the camera is on top of my car, and then we assume that the camera, the vehicle in front of me, the car, is in the same ground plane in which my own camera is. So let's say I have a camera on my car and I'm seeing a car in front of me, and this T is the location of that car with respect to my camera. So we assume that there is a coplanarity assumption here. So in this particular thing, so we managed to we managed to overcome this coplanarity constraint. So we, by reconstructing the ground plane through SLAM and forcing this car to be on the same ground plane which we are getting from the SLAM pipeline and things like that. So we were able to reconstruct cars on slopes which are not possible with the previous framework. I think so we continue to work on this problem, and finally, just to say, like, we managed to get one result in IV20.
Through this work, we propose a novel approach to perform monocular multi-body SLAM in dynamic environments.
Are you able to hear the video?
As a solution to map all vehicles in a sequence onto a unified global map in the metric scale.
So this is the final camera trajectory which we managed to get in the global frame. So I'll stop here, this particular thing. And with this.
Our pipeline takes a sequence of frames captured using a monocular camera. We initialize 3D depth to points using known camera height and metric scale. We achieve vehicle localization using a key point network, which estimates key points over distinguishable features on vehicles. We then fit a base shape prior onto a vehicle instance by optimizing for its pose and shape parameters. We obtain odometry in metric unit by scaling ego motion estimated from ORP SLAM 2 using ORP point correspondences on the ground plane using semantic segmentation. We solve for metric.
So the basic thing is that we get this from this deep network and the pose and shape pipeline. We get the reconstruction of the 3D object in the metric scale. But this ORP odometry is not in the metric scale. But what we do is the simple trick. We know the camera height, and once we know the camera height, I can get the points on the ground with respect to the camera, and those points on the ground with respect to the camera are in metric scale, and those same points are there in the stationary world in the ORP scale, and then we can solve for the scale formulation. However, we cannot do it with respect to a moving object and a stationary object because there is a relative scale there. But between two stationary, the same stationary point, so which is to say, like the ground plane as reconstructed from ORP SLAM, as well as the same point seen with respect to my known camera height. Using that, I can solve for the scale, and then we lift the OrbSlam related scale, which is in its own scale, to the same metric scale in which the moving object is represented.
Scale with an error minimization formulation on these points. The postgraph optimizer uses estimations on odometry and vehicle localization to minimize the loss computed over each cycle created in the postgraph formulation. After postgraph optimization, we get the trajectories of all dynamic bodies into one unified global frame in metric scale.
Yeah, so this is the challenge which we started off, like this, the unobservability problem. So with lots of struggle, or we can say, though this didn't get accepted in IROS, but this is one of those few papers which actually show now this vehicle trajectory and the camera trajectory is in. So this vehicle is now represented with respect to a global frame, with respect to the starting camera frame. So this is which is to say, I have recovered the dynamic trajectory in the same scale, with respect to a starting frame, right? So this is. Of course, this only works for, it breaks down when there is a rotation and things like that. But yeah, just to say, like, because I talked about a lot of things. So what I wanted to say here is a few things, just to recap. So this moving object reconstruction is intractable because we can't triangulate a moving object from a moving monocular camera. And the traditional formulations filter the moving object, and then we reconstruct the moving object, assuming that the camera is stationary, and then we reconstruct the stationary world, and we estimate how the camera is moving with respect to the stationary world. This is the standard stationary SLAM framework. We then, because we have segmented the moving object through motion segmentation with epipolar constraint and all that, so we get the camera trajectory with respect to the moving object, or equivalently, we get the object trajectory with respect to the camera, assuming that the camera is stationary. So I know where the object is with respect to my camera. I know where the camera is with respect to my ground, but these two vectors are not in the same scale, so we can't just add them up like that. So in the classical framework, we solve the relative scale problem through a particle filter method or through an analytical solution. But then repeatability of this was very tough because of the idiosyncrasies of monocular SLAM itself, and to actually get from successive observations of a moving object from a camera, having segmented the object and assuming that the camera is moving with respect to it, with the traditional classical SLAM pipelines, this was very tough and was not repeatable. Typically, for us to get the result was very tough. However, in the deep learning era, so one can have these kind of, we can learn a 3D model in terms of its basis vector and mean vector and basis shape parameters, and we know where those 3D points are in 2D because we can train a network for 2D semantic key points, and then we can try to find out the best pose and shape of this 3D. Given an image of a car and given a prior shape model of the car, I can solve for the pose and shape of the car in a decoupled way, and say where the car is with respect to my camera. So, however, the camera with respect to the ground is still in a different scale. So, though the reconstruction of the moving object is very nice and attractive with respect to the camera, I still don't know where the moving object is with respect to the ground. And with, however, if I know the height of the camera and things like that, and I get a ground plane segmentation, I can actually solve for, I can lift my stationary stationary slam camera trajectory into the metric scale, and then I'm finally able to fuse everything in one representation, which is to say, like with a single camera, as it moves, I'm able to get dynamic trajectories with respect to the same frame in which I am estimating the camera trajectory. So this is the problem, which is intractable, which I hope I conveyed, and wherein we have managed to solve it. But I think there are much better solutions than the IV20 solution which we showed here. But then finally, this is where we are, and I think there are not too many methods still there which can actually get the camera trajectory or the moving object trajectory with respect to a starting camera frame. You know, like even in this, you can say where the object is with respect to my camera all the time very nicely with deep learning, but it's still a challenge to say where the object is with respect to the global frame or the starting camera frame. So this problem, I think, is still remains to be solved, and this is one problem which we have looked at over the last 11 or 12 years. Of course, there are a bunch of many other problems which we have been looking at, but I would stop here, and I'm happy to take questions. So hopefully I will be able to answer some of them. Thank you for staying through this talk. And
okay, thank you, Madhav. Martin, can you hear me?
Yes.
Okay, cool. Then my connection is good. Okay, thank you, Madhav. Nice sort of, how to say this, tour, guided tour of dynamic slam stuff. So anybody with questions? I'm going to open this to the audience, please. What? No
yeah,
questions?
maybe I possibly, how do I see the Zoom window?
Maybe you stop share the screen on which you're sharing is a Zoom window, right?
Yeah.
Oh, okay. I think Aaron has a question, and if I know this correctly, he won't mind if I give students a chance first. Anyone else in this call wants to ask a question? No one. Okay, in which case I will give it to Aaron. Be prepared, Madhav.
Aaron, I think you need to unmute yourself.
Yes, yeah. Can he not hear us? Okay, so while we wait for Aaron to figure out his mic and come back to us, I will I'll ask a question.
So is it like, no, I mean, like possibly I should have given some introduction or slam perhaps.
No, you can't do a full lecture here. I mean, you assume that people understand basic stereo and robotics, I believe, and which is reasonable, right? Many people in the talk have taken a module or have seen something of this form before. Otherwise, your lecture would have been much longer if you had to give everything. So I had a quick question. So in terms of general dynamic slam itself, can you talk a bit when you mentioned one, right? This kind of correspondence thing, but can you talk about what are some other, say, open problems that you think people could look at if they wanted to focus? Because one common perception is, slam has been done for 15 years. What are the problems, right? Can you talk about that?
Oh, okay. So like, yeah. So I think if you say like, so this particular thing which I was saying was a dynamic slam with a moving monocular camera, right? So, but
I'm not. Let me be clear. I'm not talking about the standard robot slam stuff.
Yeah.
Right?
So let's say if you're doing, let's say you're doing lidar slam, right, and things like that. So there, I think the one of the things which possibly people would like to is the frame rate itself, right? So how quickly I'm able to estimate my trajectory and the reconstruction. So here maybe I'm not so worried about the slam problem, but I am looking at a quick estimate of the object with respect to where I am, or a quick trajectory estimate with respect to the last 10 frames, and then maybe to predict what's going to happen into the future, right? So more accurate the trajectory which I'm seeing so far. If I want to use these LSTM models or one of these deep network models to predict what's going to come in the future, I think I need a very robust estimate of this this vehicle trajectory. So, and I need it fast for me to be able to predict what I'm going to see into this future. I think if you're using LiDAR, for example, as your sensing modality, then I think typically the Lego loam or the loam framework is reasonably stable, that it gives you a reasonably good camera trajectory or a vehicle ego trajectory over the last 30, 40 frames, at least, quite well. And we are also able to segment this. There are many 3D segmentation methods, or like you can segment in 2D, and then where the LiDAR point is corresponding to this 2D image. So I would say that I'm not sure if there are significant challenges that remain in SLAM itself, but maybe quick recovery, or how fast can you solve for it is one thing. But however, what we see is, if you are making aggressive maneuvers, like for example, if you're not moving on the road, but you are flying with a drone, and you are making a lot of aggressive maneuvers with drones, then this visual inertial navigation pipeline is becoming more and more popular. But I think there is still a lot of, we have seen that when as they do tend to break when you have very sharp rotations. As a matter of fact, even LiDAR SLAM tends to break when you have a very sharp turn. So to actively predict if I'm going to do this, my SLAM would break, and to avoid this from happening. So what I would call is, maybe there would be a migration towards active SLAM, which is to say, how do you prevent a SLAM to break as I'm moving on an en-route scene? Like, what kind of motion, how do I control my vehicle in a way in an on-road scene where there are a lot of dynamic participants, and if I'm doing SLAM, that this should not break. And so this could be one problem. As a matter of fact, this is one problem which we are also looking at. And how do you handle it in terms of aggressive maneuvers for drone, or even in a car, if I take a very sharp turn, my estimates can go completely bad. Or if I move over speed breakers, or if I'm moving on slopes, or suddenly I go up and down. So how do I continue to maintain my trajectory? So everything is fine as long as the road is planar. But I think if you're moving on uneven terrain, so if I'm moving on rugged terrain, so I think the SLAM frameworks have not been tested out there. As a matter of fact, there is no uneven terrain SLAM data set, as far as I know. Maybe there is something out there, but so let's say like a tank is maneuvering in a desert, and how do you do in that featureless world? Can you do SLAM, or you have a vehicle that is moving through a sand dune?
Madhav, I had one other. Sorry, didn't mean to interrupt. I just realized a question. Yeah. So if we were to take, so you keep talking about all these sort of exceptions, right? Like when things change suddenly and things like that. So even with the deep network and other things that you're using, do you not have trouble that you may not be able to train for all these situations in advance, even for the problem that you are working on? One of the final results you showed was okay, I presume you do with all these benchmark data sets and stuff. But even if the system were working and you had, say, I don't know, any of the examples you just mentioned, like sudden change in trajectory, or the plane on which the so-called robot or the car is moving, and if these things happen, do you not have similar trouble even with that, even with sort of all the training and stuff?
I agree.
And if
so
you
that's
have, how do you solve it? I mean, yeah.
So that's why we had this solution for the slope problem. As a matter of fact, when I actually showed this to David Scaramuza when he came to IIT Madras, and I showed him, and he's the big guy in SLAM, and he told, hey, no one has shown that kind of result so far. But we couldn't pursue that because the students leave. But yeah, I think that's a good point. So if you're moving on a hill, if you're climbing down a hill, but I think the object recognition may still work. But what's going to happen here is normally all these methods which reconstruct, which are especially the single view depth methods, which I didn't cover it here. So you have a bunch of single view depth methods, right? But they all, I think, are working with respect to fixed camera height and with some coplanarity assumptions. So suppose I suddenly take those pre-trained models and move on a hill, and with vehicles moving with respect to me on in slopes and curved slopes, I think that wouldn't work. So I do not know, sir. Maybe we need to. I don't think this networks would directly translate that. That is my.
I'm asking this because I have friends who do this. These days, these self-driving cars is almost every other company wants to build this, right? So these are some of the things that they show where they have troubles. I was just wondering, like, if you have thought about similar problems.
Yes,
I'm not expecting a solution. I'm just looking for sort of open problems that you think would be interesting.
I think the slope is certainly a problem, or reconstructing where you have uneven terrain or upslope, downslope, moving on hills. And the IROS 2018 paper actually does talk about that, how to do it, but we didn't have a data set at that point of time, so we had to make use of Cynthia, and Cynthia is closely models the San Francisco road scene, so where there are a lot of slopes, and we kind of showed it worked in a synthetic data set, and in Kitty also where there were some slopes, but we didn't have ground truth on Kitty. So yeah, I think that is one challenge. We don't see a lot of drone data set, like where drone flying with many cars moving. So how do what happens in those kind of scenarios? So typically when the camera pose with respect to the world changes, I think the deep networks may not hold. And most of the data sets are with respect to a camera at a fixed height on the car and moving on flat terrain. So when this assumption is removed, I think there is a lot of open problem.
Okay. Good. So just to give you, I'm sure it will be a drastically different question. So I'm going to call on Aaron. He's a very senior researcher. Come on, Aaron.
I'm sorry, my system has been crashing for unknown reasons, but it sems to be concerned with
We can
videos.
see you and hear you fine, Aaron. Please go ahead. Yeah.
Anyway, I was wondering whether you've taken, or anyone in the field has taken account of the enormous trouble evolution seems to have gone to provide inertial sensing in animals, in particular in humans. And obviously it's not going to solve all the problems, but it can perhaps make a major contribution. I'm talking about these semicircular canals and so on, and you can easily disrupt people by disrupting those things, as I have discovered myself at times.
So I couldn't get that question. So you said about inertial sensing, right?
Yes, and in animals, the semicircular canals.
Okay.
Do a very important job with, especially, I mean, certainly in humans, and presumably to some extent. And so you know inside yourself when you're swerving, whether you're accelerating or decelerating, which way you're swerving, and so on. And that could help if we could somehow get technology with similar powers, and maybe there is, I just don't know. But if that could be replicated.
Yeah, I mean, as a matter of fact, visual inertial SLAM, wherein we have this hardware coupled cameras, which give camera images and the inertial measurements at the same synchronized with one another. So there is a lot of research which has already happened in what we call as bins, visual inertial navigation system, where these IMUs are used, the pre-integrated. So we have this IMU motion models which are getting pre-integrated, and they are combined along with the visual reprojection frameworks to come up with a better estimate for monocular camera. As a matter of fact, that is the way to go, because monocular camera trajectories are prone to break down in various ways, especially when you have these very sharp rotations, which we are just talking about. However, I think the inertial, if you are able to couple it with an inertial estimate and with pretty good, if you have a very good bias of this inertial sensors, the acceleration bias, we are able to estimate, and we are able to keep integrating the IMU between two successive frames at which image comes. And if I'm able to estimate where my camera is through this IMU pre-integration at the time when the new camera image comes, so that is shown to be a lot more reliable and successful than only using a single camera system. I don't know if that answers your question partly, or
I don't know to what extent that technology replicates the functionality of the animal system, but perhaps it does more than I suspect.
This is the standard inertial sensors which measure the acceleration in 3 degrees and the gyroscope rotations, which has been there in space. I think now it's popular in. There are a lot of MEMS sensors which do that, and when coupled with cameras.
Right.
Yeah.
So. Are there any other questions? Because if not, I can ask another one.
Just a minute, Aaron. Let me just check. Anyone else with any questions, please?
So Aaron Sloman is a very famous. Is that the same famous person?
Yeah, he even has a lounge named after him. I should mention this.
Right. Yeah, I'm very humble.
I've been around a long time and made noises at various times, and I still haven't solved the problem that got me into AI in the first place, which was related to the question I was going to ask, which is humans, as I expect you know, but very many scientists and engineers and mathematicians do not know, for thousands of years made discoveries in geometry and topology by reasoning spatially, as improving things like Pythagoras theorem and all that other stuff that's in Euclid. Are you familiar with ancient geometry? I mean, do you know what I'm talking about? Okay, so
sorry,
well,
I'm very poor with especially modern Riemannian geometry, differential geometry.
No, I'm not talking about modern geometry. I'm talking about how people used to prove that the internal angles of a triangle add up to a straight line.
So Madhav may be surprised because I'm sure he went through this. He's talking about the kind of stuff we learned in school, Madhav. Don't worry. It's
without coordinate frames, not the coordinate geometry, but theorems and riders without. I mean, I know what's the vertical angle theorem and things like that, but not beyond that.
What worries me is that many people now do not learn at school to do those kinds of things, and as a result, they do not know that it is possible by spatial reasoning to prove certain things are impossible or necessarily the case. And so I get people all around encounter people all around the planet who think that spatial reasoning has to make use of neural nets that learn things and collect lots of statistical data, then derive probabilities. And that will never give you insight into what's impossible. It may give you a low probability, but that's not the same thing as impossibility. For example, I mean, just a simple case, a young child will know that if you have, I don't know if you can see what I'm doing, I've linked I've formed 2 rings linked, and a young child will understand that no amount of just moving these things around relatively without changing the shapes of the individual links will separate them. And that's a kind of impossibility as opposed to low probability. And so this may be not really appropriate for your talk, but I like to ask researchers, are you incorporating any of the kinds of ancient reasoning that doesn't work on statistics-based neural nets, but does work on spatial understanding of structural relationships and their constraints? And it's from the way you've been reacting. I suspect it's something you just haven't thought about, but maybe if you do now, you'll come up with a great new breakthrough.
I mean, so I think not at the same level of profundity, or at the profound level possibly which you are you are possibly coming from, but we have, as a matter of fact, we have used, even in this talk, I was talking about how the car moves with respect to the stationary world as a way of detecting motion in terms of shear and stretch, wherein we were not the relation, the spatial relation which is there between the car with respect to the background was used to solve the motion segmentation problem. I did say in way. As a matter of fact, I think I can play this video. I mean, just I know if.
And with luck, it won't crash my system. I don't know what's going on in my machine. Yeah.
So over here, we kind of allude to that in some way, but not. I don't think maybe.
Okay.
I think you might want to share your screen again.
Oh yeah,
yes, Madhava, we're not seeing anything yet.
Yeah, I have not started. Also, I'll share the screen.
Okay.
I'm just searching for it because
I'm going to keep my head moving so that if it freezes, you'll know I've crashed out.
So are you able to see the screen?
Yes, I see. Yeah.
Yeah. So here, so this is the thing. Let me go into. So here we have this. Let's assume for some things these green and red dots are some motion models, so what we call as affine motion models, and we want to say whether they are the same, they belong to the same motion or not, because they belong to the background. And so here we say that even as I keep moving, there is not much shear and stretch between these two motions, and we are merging them. Whereas so we say like this belongs to the background because they don't have a lot of shear and stretch between them. But that here they are, and therefore we don't merge. So this was used as a matter of fact to overcome state estimation issues we face. Like, like otherwise to do this motion segmentation, I need to estimate the ego car motion, not the car in front of me, but my own motion. Now we avoid that by bringing this relation which this enjoys with respect to the background, and to make use of that to say whether this should be merged with the background or not. So I don't know if that has some relevance to what you were saying, but there is this kind of relation, the geometry relation which this has with respect to background, things like that.
If I've understood you, it is exactly related to what I was talking about, except in this case, I presume the geometrical theorems were sort of plugged in by the researchers. The system did not have its own ability to discover a spatial impossibility and to make use of it in that way. Yeah.
Yes. Yeah.
Thank you.
I think we should wrap this up. We've gone on, and I know Madhava is 4.5 hours ahead. His probably stomach is rumbling. So
yeah, I hope. I sorry, like if I went through very fast, or I mean, this is a problem. I hope maybe I should have spent more time on one rather than so many things.
So I'm going to still give one last chance. Anyone with any final questions? If not, I'm going to. Anyone? Sorry.
Yes, so I had 2 questions, but they were already answered without me
Then you don't have any questions.
So thank you very much for the talk from my side.
Okay. So
thanks a lot, Martin. Thanks, Mohan, for inviting, and thanks, Aaron.
Thanks for this nice, how to say, this guided tour. Like, oftentimes with something like, especially with visual and this dynamic slam thing, it's very difficult for someone to understand what's going on and what the problems are and so on. Because as you know very well, there are less, there's a lot of individual samples, but oftentimes they're not sort of like, it's very difficult to figure out which ones to follow and which ones to keep track of. So this was a good guided tour. Thank you for doing that.
Sure, yeah, thanks.
So I'm just going to say thank you, and I think he can hear me, so I will be the audience member clapping.
Yeah, thanks, and thanks, Martin, and thank you. Sure.
Thank you, Madhav.